Welcome. In this session, we'll explore decision-making with analysis of variance, one of the most popular techniques in the social sciences. Here, our learning objectives are to understand how the analysis of variance can help us understand trends and differences between populations, how we can use one or more factor or variable to help us understand those trends, and we'll also be looking at pairwise comparisons to see important details about those trends. It's not our differences that divide us, it's our inability to recognize, accept, and celebrate those differences. A great quote from a human rights activist and author, but it's also appropriate for Anova because it helps us understand differences, and hopefully those differences are important and make an impact on business or on general well-being because the differences are detecting helpful therapies or other kinds of outcomes. So let's take the situation where we have gathered a sample of workers' wages earned per hour. For this example, this will be in US dollars. And if we have this sample of salaries or wages earned per hour across this sample of workers, what is the best way that we could describe this population? Well, we've actually spent a lot of time in this class thinking about that. The best metric that we can use to describe a population that our sample is drawn from is effectively to use the mean of the sample. The overall average is the best score that we could choose, and if we use that score to then predict it for each of these observations, so using the mean of 12.26 here and here and here, it can be shown statistically that that is the most effective way to predict all of the scores. But there's going to be some error, and we call that error variance. That's going to be the difference between the actual observed score, or in this case, wage earned of $12.10, to what was predicted for that person, $12.26. So there'll be some difference. So that 16 cents in this case is error. And you can see that there's going to be some error across the entire set of wages. Not exactly has anyone really earned $12.26, but that's the prediction. And we've learned that from our univariate analysis of variance that the mean as a measure of central tendency for any variable is really the best way to understand it overall. And we can compute other things like the standard deviation and the variance. But that is the way that we could best describe the population from our sample, is to use the mean. However, so the situation looks something like this. This is our sample, this is the population that we're predicting, and just here's all the values, basically just a visual picture of what I just discussed. However, if we know something more about where those numbers come from, could it help us improve our prediction? That's really the question. So what if I told you, instead of just looking at everyone as a total sample, what if I told you that some of these wages came from workers earning per hour in London and in Munich and in Paris? What would we intuit about the wages earned? Well, for some of us, it might be obvious that even though we want to now maybe compare the differences between wages earned in the different cities, there's something unique perhaps about the scores that would help us make this prediction better. And so let's explore that a little bit. We want to understand if there's a significant difference in the wages earned between the cities. But we see that there's this other sort of trend that we're almost ignoring when we're trying to detect these differences, and that is earnings within workers in London may be more similar to each other than earnings within workers from Munich. And again, different from earnings within workers in Paris. And so knowing that information could actually help us detect a difference between the cities, which is really what our question is. Are workers between these three cities earning something different? So by obviously acknowledging that the salaries earned within London are likely to be more similar within each other, knowing that information, it might help me predict better the differences between the cities, because I would be able to account for the variability that's attributed to the workers within the city before I try to detect a significant difference between the cities. So this is a very important concept. Now, looking at these from this example, where initially it was just a collection of wages earned, it may not be obvious how powerful this new information is, that some of the values that have been identified come from workers from one city. So let me illustrate this with a few other examples. What if instead of wages earned, it was actually drugs that were being issued in terms of therapy? If we knew that all of these patients were on drug 1, and all of these patients were on drug 2, and all of these patients were on drug 3, and I'm trying to detect the difference between the therapies to compare whether drug 1 is better than drug 2 or drug 2 better than drug 3, you could see how important it would be to understand that variability within this piece of the sample, almost think of it as a subsample of the whole. These patients may be more similar to each other because they all received drug 1. And I would want to use this information to help me then compare them to a new subpopulation of drug 2, and similarly to drug 3. So this within patient variability that I can explain because they were all on drug 1 is super powerful, and then it helps me detect a difference between the other drugs. Another example about within, what if I told you that these were measures of mental acuity? And if I knew that everyone in this subsample actually consumed coffee, this subsample they consumed beer, and this subsample they consumed water, it would be obvious that if I wanted to detect a difference between these three groups, knowing that all of these folks had consumed coffee, beer, or water is going to help me make my prediction better. This is exactly the situation that Anova has been designed to help us. It helps us understand variability within groups before we try to detect differences between them, which is really what we're trying to understand. Because we want to know if our situation is being driven more by some kind of sub-average that we can determine is actually happening between our groups, going back to the wages and city example. And so we don't have to just look at the overall average, which we can still calculate in the sample. Instead, we can use the power of the information that we have that each subgroup has a mean. And therefore, there's variability that I can attribute just to the element that's related to that particular group. In this case, it would be salaries in London maybe are significantly different for some reason, and workers there are different than salaries in Munich, salaries in Paris. So the picture that I'm trying to determine, is it more like the first situation where all the values are just grouped together and I just have to predict one mean value for all of the workers that I've sampled, which would basically mean that they're from all the same population? Or do I have a situation that's more like this, where I actually have maybe 3 different populations that the sample is giving me information about? And instead of just using the general overall average for all of the salaries, instead I can utilize the variability within to help me detect the difference. Because I can almost account for or control for the variance within the groups, which might be clouding the ability that I have to detect the difference between the groups, which is really what I want to know. So the test that's going to help us do that is analysis of variance. It's called the F test, and this is exactly the ratio that's calculated. We want to detect a difference between the groups by looking at the variability, the differences in the means, the sample means, between those groups. And we want to control for or factor out, in a way, the variance within the groups, because I can understand the variance within those groups a lot easier. They were all from the same city, or they are all taking the same therapy, or they were all drinking coffee, for example. And those things I can understand, and it might be affecting my ability to actually detect the difference I want to know, which is between these groups. So this is the ratio. The F ratio is literally within group into between group. So hopefully if these values here are relatively large in the sample, we want to sort of factor those out and have that controlled before we're looking for a difference between the groups. And a large F ratio is going to help us do that. It's going to account for the differences within the groups So to take that out of the way, and let us just really peer at the difference between the groups. So this is the hypothesis, of course, is that there's no difference between any of the groups in the sample. If this is the case, if the null hypothesis is true, we might as well just predict the mean for the entire sample and not pay any attention to the groups, because knowing something about those groups have not helped me make a better prediction. I better just predict that they're all from the same population and use the overall mean, which we showed you in the very first slide, which is just the overall average for every measure in my sample. On the other hand, the alternative hypothesis is going to be not all the population means are equal. That means that there could be a significant difference between, in this example, Paris versus London, or London versus Munich. Any of those things could be detected as a significant difference. And that would tell me that not all the population means are equal. It would look much more similar like the slide previously that showed 3 different possible populations. So we want a very large ratio here, which is going to help, as I had shared before, control for, in a way, the variance that I can attribute within the group and make me see the variation that's between the group. And then we want to reject the null hypothesis, meaning that at least 2 populations are significantly different. This is very familiar sort of thinking to the z-test. Just because we're calculating a new statistic, it doesn't change the fundamentals of what we're doing in the class. Effectively, if we have a ratio that's large enough, we'll have a large F value, and we will be setting a significance level that it should be relatively rare. Again, it's going to be typically it's going to be at that 0.05 level, that if the null hypothesis were true, we would not observe a value this large or larger any more than 5% of the time out of 100. And knowing that we have a very large F statistic that's very rare, if the null hypothesis were true, allows us to then reject the null hypothesis and determine that this value, whatever we had observed that created that ratio so large, is significantly different. And in this case, it's going to be different because we've controlled effectively for the within variance, and we're paying a lot of attention to the between, and this between level is significantly large. It's very weird, and weirdness in this case is a good thing, so we can reject the null hypothesis. A couple of assumptions that we need to keep in mind. We've been spending a lot of time in the course looking at the normality of our variables from a univariate perspective. Those are all the questions that we were asking about every individual variable and how normal it is. That's very important in Anova. We want our dependent measure, which some call a response variable, whatever the dependent variable is, to be normally distributed. In our example, that would be the wages. So for us to apply Anova appropriately, we would want the wages to be normally distributed in the population that the sample is from. We would also want homogeneity of variance. This is to say that the samples that we're taking and the subsamples have equal amounts of variability. So think of this in our example, we would want and assume that the subpopulations of London and Paris and Munich, those also have equal amounts of variability. There's nothing unusual about that subsample across the populations that they come from. And so we can then test for differences by understanding or assuming that this is true. And lastly, we want independence from one sample to the next. So again, if you think about this in terms of the wages that are earned in London, the workers earning those wages, they don't have any direct impact on the workers that are earning wages in Munich. And the workers in Munich have no direct impact or influence on wages that are earned in Paris. That would be an example of independence. And so we can assume that they are in place, and we can test for some of these things and make sure that that's true when we use Anova. We also typically for this, we want our dependent measure in Anova to be a scale or a scale variable such as ratio or interval. In some cases you can use ordinal ranks, but the typical case is going to be a ratio or interval scale. In our example for the wages, that's a ratio scale. It has an absolute 0, and there's a meaningful progression of values one to the next, and so that's the most common situation for Anova. If you don't have this situation, you're more likely to get value out of using a chi-square, such as for categorical variables. Another assumption is that our independent measures are usually nominal or ordinal. They have distinct groups: Paris, Munich and London are nominal. There's no order to them, and we can fully understand which group that they're in. In some cases, you may see some ordinal variables used as independent measures as well. Now, can you use a scale variable like a ratio or interval scale with Anova? The answer is yes, you can, but it's beyond this session to cover that. It's going to be a different kind of an instance for Anova, in this case called Anova. And there's other kinds of things where you can mix both categorical and continuous variables. But for the most part, our independent measures, they're going to be categorical, nominal, or ordinal. And we will have dependent measures that are typically ratio or interval. That's the most common application for this test. A few other assumptions here. Most of the time we're in social sciences, we're doing a lot of observational studies, such as the difference in wages between Paris and Munich and London. But you could also be doing an experimental study. Oftentimes with big data analytics, we have a lot of web companies that are doing experimental designs. And certainly you would see Anova being used in traditional lab studies, such as testing therapy. Drug 1, 2, 3 would an example of that, with randomly assigned folks to each drug condition. When we're randomly assigning people and we're controlling for other factors and making sure, for example, in the drug study, everybody in drug 1 group is getting only drug 1 and they're not getting drug 2 or 3, those would be controlled for factors that we could look at in Anova. And it's much easier to decipher cause and effect relationships when we're using experimental studies to do that. Observational studies are a bit more difficult. There's no attempt to control for factors. So in my example today, we never randomly assign workers to the city of London, Paris, or Munich. So we don't really have any ability to do that. It's an observational study, so we're just looking for differences. I see both of these very common situations in the social sciences and in businesses, and a lot of times we're doing really observational studies. And so we're not able to really control all those factors or randomly assign people to conditions. Again, if you're using a web situation, oftentimes now experimental designs are often done. Facebook has been reported at any one time to have as many as 10,000 different versions running. And as those are run, people are effectively in experimental conditions, and so Anova could be used to do that. But if we're just looking at web traffic across days and we're not controlling who is visiting, that would be more like an observational study.